Alright, let's do problem about maps and stuff. Okay, so what is the point of this problem? What do we have to do? We must prove that GR is a subgroup. I learned you can of writing subgroup using a less than sign. But I don't know if this is standard notation, but I'll use it just because it means I have to write less. But anyways, so we must prove that GR is a subgroup of the symmetric group on G, because that's what it means to be a transformation group. And so, let's see here, the identity map 1, which is 1R, and that's just multiplication on the right by 1, and that's going to be in GR. So, got that. Do we have to verify that this is 1? I mean, if you have to do it, go ahead and do it. I'm not going to do it because it's very straightforward. For all A, B, and G, and R. What is AR of BR? It sends X to, let's see here, BR will send X to XB, and then AR will send XB to XBA. So AR of BR is equal to BAR, which clearly is an element of GR since BA is in G because G is a group. Next, for all J, A, and G, AR of A inverse R sends X to X A inverse A equals X. So AR of A inverse R equals 1. So likewise, A inverse R of AR equals 1. So the inverse of this element is just given by A inverse. The inverse of this element in GR is equal to A inverse the element in G sub R, which is clearly an element of GR. And so that finishes it, right? So hence GR is a subgroup of the symmetric group on G. So now what? Now we need to prove that this map is an isomorphism. So next, define a function. I'm going to give it a name, and I'm going to call it capital Phi. Phi from G to GR by, so your phi of A. Yeah. Now, when Jacobson does arrows, he means like this is where you send the element X to the element XA. I don't like that notation because I like to be able to write arrows like this, where like you have phi, and this shows that phi is a map of that sends elements in G to elements in GR. And if I want to show what it does to particular elements, I'll say it takes A and sends it to AR. And so I use this vertical line at the end of the arrow to show that we're talking about elements and not the sets. But whatever, to each his own. So define this by, this is AR inverse. So this is the inverse of the map AR, and not the element A inverse sub R. So this is clearly a bijection, or rather phi, or phi, whatever. It's clearly a bijection. And why is that? That's because if you have, you can just sort of check it. Certainly, if you take any particular element of GR, because GR is a subgroup, it's going to be the inverse of something else. And whatever that inverse is, it's going to be represented by some A and G, and so it's pretty easy to see that this is surjective. Then for injectivity, you can just say like you have A and B are different values, and you consider where phi sends them, and then those two maps will send the element 1 to different places, because one of them will send 1 to A, the other one will send 1 to B, and of course A is not equal to B, and so this is injective. So if you want to write it out, you can just basically do exactly what I just described. But I think this is enough here. We do have to scroll down a little. Okay, so it's a bijection. We want this to be an isomorphism. Right? Yes. So it's a bijection. And so what else do we need? We need to send 1 to 1. Phi of 1 is 1R inverse. Now, what's the inverse of the identity map? It's just 1R. Okay, so that's good. How about the other big thing about homomorphisms? Where do we send AB? We send AB to AB R inverse. And we proved previously that. Now, I was being a little fussy earlier when I was saying like this is AR inverse rather than A inverse R, but we showed earlier that these are actually the same thing, so it doesn't really matter. So let's see here, AB R inverse. So this we know because we proved it previously. This is equal to AB inverse R. And what is that? AB inverse is equal to B inverse A inverse. Always in a group. R. But then we also discussed how multiplication works. Remember? AR of BR equals BAR. So B inverse A inverse R is going to be equal to, by the same logic as before, A inverse, here I'll put parentheses, A inverse R of, come on computer, this is my first video of the day and I've got like 5,000 more to do, so can't die on me now. So this is equal to this, but that's just phi of A, phi of B. Of course, multiplication here is composition, whatever. So hence, phi is an isomorphism. Now that I'm looking at it, I feel like there's something that you could do here with like isomorphism theorems to make this really easy. But I don't think the proof would be shorter, and you won't be able to use techniques that have been covered just in section 3 for that. But anyways, here we go. Here's the proof, and we are now done.